Hi, so here we are in the third chapter. Now, the third chapter's goal is to go over three short sections here, languages, grammar, and graphs, that a person probably already has a good background in, but just trying to establish some basic vocabulary, a few basic ideas, and make sure everybody has the background needed for the remaining two chapters, chapter 4 and chapter 5. Okay, so let's get going on the first one on languages. So you may want to review the material that is in the appendix on strings, really basic vocabulary, but just to make sure that everybody's using the same vocabulary. Here is some of that material reviewed for you already, but there's more in the appendix. So a symbol or a token is something that a machine can read and write, and you just really think of it as a bit sort of thing, or a letter like a ASCII, lowercase a kind of thing. An alphabet is a non-empty and finite set of symbols. So ASCII, or maybe Unicode. A string or word over an alphabet is a finite sequence of elements from that alphabet. So if you have the letters A, B, C, lowercase a, lowercase b, lowercase c from ASCII, that's a finite sequence of elements from that alphabet. The string with no elements is called the empty string and is denoted here with the Greek letter here, epsilon. There we go, the Greek letter epsilon. And we'll reserve that symbol for the empty string. We will write symbols in a distinct typeface. So that's a kind of a typewriter text, and a typewriter text, you notice that the A here looks very different than the A here. Because the alternative of quoting that would be clunky. If you tried to say the symbol 1, and every time in the book you wanted to say the symbol 1, well, that's just simply clunky. Now, traditionally, alphabets are denoted with the Greek letter capital sigma. In fact, that's pretty universal, so that if you go to a talk and somebody writes a sigma, that they won't even bother to say that that's the alphabet. We'll name strings, in this book, we'll name strings with lowercase Greek letters and denote the items in the strings with the associated Roman lowercase letters. So for example here, this is a Greek letter sigma, and then I'm using S0 through Si minus 1. See how that's a sequence of characters, S0 through Si minus 1, as the members of sigma. So that's the Roman lowercase letter that's associated with the sigma. And here is tau and t's. If you have a string sigma, then the length is the number of symbols that it contains. This particular string happens to contain n symbols. And in particular, the length of the empty string is 0. Now you notice that we use vertical bars for length, anytime you want to describe somehow the size of something in mathematics. Use vertical bars, so the appropriate thing for size in a string is the length. For small scale examples and for exercises, we're not going to work, we will typically work with examples that are not really taken from real life languages kind of stuff, but instead we'll use like letters A, B, C. So it's awkward then to use the brackets and the commas. It's just a pain. So instead, we're going to write, we'll just write ABC here instead of open diamond brackets, A, comma, B, comma, C, close diamond bracket. It's just a question of getting work done, that's all. Again, everybody does that. You'll see that all the time. Natural numbers, of course, are represented up by strings of digits, and so what you're looking at there is that the symbols are things like 0, 1, 2, and the alphabet is the collection 0 up to 9. So that the string sigma equals 1066, and again, notice the distinct typeface, has a length of 4. And in the book, we refer so often to the string that consists of the 0 and 1 characters that we have a special symbol for it. That's called blackboard bold. But anyway, it's that funny looking B. And it consists of the characters 0 and 1. And strings over that alphabet are called bit strings or bit strings with space, but we usually write it without a space. Okay, so really a lot of vocabulary, and again, some of it may be unfamiliar to some people, but most of it is pretty standard. Okay, string operations. So if you give me two strings, if you give me sigma and tau, then the concatenation is where you just append them together. So sometimes you write a little, what looks like a little frowny symbol, or sometimes you just simply write the one next to the other. The frowny symbol is sort of more distinct. So if you want to say, you know, don't mistake that there's a concatenation here, you might use that symbol. I often do that. And you just simply put the characters of the first, comma, and the characters of the second. That's just that straightforward. So if you have sigma and you decompose it into a concatenation of things, then you say that that each tau I is a substring of sigma. So substring. The first substring is called the prefix, and the last substring is called the suffix. Now, a power of a string is an iterated concatenation with itself. So if you say something like sigma concatenated with itself, you might call that sigma squared, or sigma concatenated with sigma, you might call that sigma cubed. I'll note that there's no parentheses here because it doesn't matter whether you do it the first two first and then the third, or the second and third first and then tack the first on the beginning. It doesn't make any difference, so I haven't worried about that. In other words, string concatenation is associative, and I'm not going to worry about it. Just for consistency, we'll write sigma superscript 1, sigma to the 1 to be sigma, and sigma to the 0 to be the empty string. And then the reversal, superscript r, of a string takes the symbols in the reversal order. So you see here that sigma superscript r starts with the last character and then goes over to the initial character. The empty string's reversal is the empty string. A string that equals its own reversal is called a palindrome, and that's a word that people often know, palindrome. And the issue there is that there are, in some sense, two different kinds of palindromes. This is where you take AB and you reverse it and you write that down as the second half, BA. But that sort of doesn't happen here. That is to say, an even length palindrome is in some sense different than an odd length palindrome, and sometimes will matter when we move through paying attention to the different things that can happen with strings. And then I want to define what it means to say the kth power of an alphabet. So if you take an alphabet, the set of length k strings over that alphabet is called the kth power of the alphabet. The set of strings of any finite length. So if you throw together all of the kth powers, you get something called sigma with a superscript star. And that's just throwing together sigma to the 0, sigma to the 1, sigma to the 2, etc. And that's a sigma star. And that asterisk is called Kleene star. And would you just read it out loud as the word star? That's all. So, for example, the set of length 3-bit strings starts with 0, 0, 0 and goes all the way up to 1, 1, 1. And the set of all bit strings then is just B star is you throw in every possible, all the length 0-bit strings, all the length 1-bit strings, all the length 2-bit strings, etc. Okay. So again, vocabulary, just trying to make sure everybody is on the same page. Okay, and then languages. So a language over an alphabet is a set of strings drawn from that alphabet. So that is to say that a language is you just take any subset of sigma star. So you write down all possible strings of characters in that alphabet, and you take a subset, an arbitrary subset. Doesn't have to make any sense at all, just some subset. So for example, if you take the alphabet to be A, comma B, then one language is the set of all strings that have the form A to the N, B, A to the N. Okay, so there are N many A followed by B followed by N many A's, and you've noticed, right, that it's the same N in both places. So you might have, for example, 2 A's and then a B and then 2 more A's. You might have 1 A and a B and 1 more A. You might have 0 A's, a B, and 0 A's. You never have 2 A's, a B, and 3 A's. It's got to be the same before as after. Another example of a language is the language of palindromes. It's a set of all strings that are equal to their own reverse. Okay, so still more examples here. If sigma consists of the 2 parentheses symbols, then the set of strings of balanced parentheses is a language. So, for example, just to pick one of the examples here, this is a collection where the set of parentheses is balanced. You see here, that's a substring with balanced parentheses. This is a substring with balanced parentheses. And finally, we have the outermost parentheses that are balanced. It's never the case that there are more closed than open parens. Okay, and then operations on languages, and we're just going to go through the concatenation of two languages is the set of concatenations. So if you give me if you give me here a first language that consists only of digits and a second language that consists only of the ordinary lowercase letters, well then what's in the concatenation of the languages will be strings that start out with digits and end with lowercase letters. And then for any language, the power, L to the K, is the language consisting of the concatenation of K many members. So if you want to look at, for example, L to the 3, then you're going to have, you take 3 things from L and concatenate them together. Doesn't have to be the same thing every time, can be different things. In particular, just to make the notation convenient, L to the 1 is L. And for k equal to 0, it's convenient to take the 0th power of a language to be the set consisting only of the empty string, because the empty string is sigma to the 0. The Kleene star of a language, this is the most important definition here on this slide. The Kleene star of a language is the language consisting of the concatenation of any number of strings. So there might be 7 strings here, or 12 strings here, or 12,000 strings here. There might also be 0 many strings. So this includes the concatenation of 0 many strings. That's a case that often gives a person trouble. You know, oh, I forgot the 0 many possibility. That I've done that many hundreds of times. Okay, so that the empty string is in L star if L is not empty. Okay. And then finally, the reversal of a language is the language of the reversals. So it's all the sigma to the R, where it's all the reversal of sigmas, where a sigma is a member of the language. Okay, and then last slide for this video. I want to draw a distinction between 2 things about a language, about what a machine does with a language. So we say that a machine decides a language. We've already talked about this. A machine decides a language if that machine computes whether or not the input is a member of a language. So you might, for example, have a machine that if you give it an even number, it outputs 1. If you give it an odd number, it outputs 0. And we would say that that machine decides membership in the set of even numbers. You could have a machine that decides membership in the set of prime numbers, or a machine that decides membership in the set of roots of some fixed polynomial. However, there's another possibility. We've already seen the distinction between computable and computably enumerable. So I'll remind you how that goes. A set is computable if you can tell whether a given number is a member of it or not. A set is computably enumerable if you can tell if a given number is a member of it, but telling that that number is not a member of it might not be possible. So there are, besides decides, there's another case. So we've done the decides, but there's also another case. We say that a machine recognizes or accepts or semi-decides. Accepts is a common word. A machine recognizes or accepts a language when, if it's given an input, then if the input's in the language, then the machine will compute that fact, maybe printing out the word yes. But if the input is not in the language, then the machine might be able to, but it might not be able to say, no, this is not in the language. However, the machine will never incorrectly say yes. If you give it 17 and 17 is not in the language, you know, the string 17 is not in the language, why the machine will never incorrectly say yes, 17 is in this, the string 17 is in this. The machine will never do that. The machine might explicitly determine that the thing is not in the language, or simply fail to report a conclusion, and you can imagine one way it fails to report a conclusion is by failing to. Okay, so just as an example, we can mechanically decide the language of perfect squares. If I give you a language of perfect squares, S will be, and we got to represent the perfect squares somehow. So I'm going to represent them with strings. So there's the empty string. There's a string consisting of a single 1. There's the string consisting of 4 ones. The string consisting of 9 ones. I'm tired of writing the ones already, etc. Now we can easily write a Turing machine that will somehow respond to this by correctly printing out, say, a 1 when the given input is in this set, and printing out a 0 when the given input is not in this set. There are, however, of course, computably enumerable tells us, there are, however, sets where the machine sees the input, correctly recognizes things that are in the set. But if you give it something not in the set, the machine is simply not able to correctly recognize it's not in the set. The machine will never incorrectly think it is, but the machine is not able to respond by saying this is not in the set. Okay, so that's the difference between decides and recognizes. And again, a very common word for recognizes is accepts. Recognizes is better, but accepts is common. So decides means yes or no. Recognizes means yes for sure, never incorrect, yes for sure, maybe not no. Okay, very good. All right, so next time we're going to talk about grammars. The definition of language here says that a language can be any subset of sigma star, but in practice you often see languages that follow rules, and the rules are called a grammar.